Okay, so in this video, we're going to focus on bonding and Lewis structures. So if it's been a while since you've drawn a Lewis structure, I'll run through a few. Um, the two types of bonding that we're going to focus on in organic chemistry will be ionic and covalent. With ionic bonding, we've got a situation where valence electrons, and so again, talking about main group elements, valence electrons are either donated or accepted. So if you're donating valence electrons, you take on a positive charge, right? You're losing negatively charged things. If you're accepting somebody else's valence electrons, then you're gaining negative charge. So an example of this might be something like lithium fluoride or ammonium nitrate, something where you've got a positively charged species, a cation, and a negatively charged species, an anion. Usually with ionic compounds, but not always, usually you'll have a metal and a nonmetal. The ammonium ion is a nonmetal cation, sort of like our celebrity nonmetal cation. But it's usually pretty easy to tell with an ionic compound or a salt because there's usually a metal that's electrostatically attracted to the cation is electrostatically attracted to the anion. With covalent bonding, it's a little different. And so this is a situation where we're going to share valence electrons. Between the bonding atoms. So they can be shared evenly or they can be shared unevenly. So for example, we could have like equal sharing, like totally equal sharing. So the difference in electronegativity between the bonding atoms is 0. So something like H2 or O2 or something like that. You could have near equal sharing. So this would be considered totally, by the way, nonpolar. There's no difference in electronegativity, then one atom is not yanking on the electron density um, in the sharing. So in the covalent bond, one of those atoms won't be yanking on those electrons more fiercely than the other because they're the same, right? Their electronegativity is the same. So that's completely nonpolar. Then we have a situation where you have near equal sharing. Usually we only say equal and unequal. I want to make this distinction because there are elements where their electronegativity is so close, but still there's a tiny bit of a difference. And we refer in organic chemistry, we refer to these bonds usually as nonpolar, but they're relatively nonpolar. If you want to be super picky about it, if you're not the same element, you have, the potential to be yanking on electrons a little bit more fiercely than another element. So carbon and hydrogen is usually a pretty good example of this. Your difference in electronegativity between those two bonded atoms is small, like super small, So carbon and hydrogen, the difference between those two is probably like 0.1 or 0.2 instead of like 1.5 or 1.0 or something like that, right? So you could have something like CH4 or C6H6, like benzene, right? And this is going to be relatively nonpolar. And truth be told, when we're going through these compounds, we usually lump 1 and 2 together as just nonpolar. And then there's the third, where we've got unequal sharing. So you've got a difference in electronegativity that is not large enough to be ionic, but it's a pretty decent amount to cause sort of the electron density to be residing down one particular side of the bond, right? With the more electronegative element. So, but not large enough to be ionic. And you could use, for example, hydrogen fluoride as an example of this, right? Um, we could use like an alcohol. So we've got methanol. So we'd be describing the polarity and the bond between the oxygen and the hydrogen. So if you're looking at the periodic table, and as you go, across from left to right and up, you'll notice an increase in electronegativity, with oxygen being more electronegative than hydrogen. If you need a number to go by, so these are not quantifiable things. This is just sort of like an observation we make about the behavior of these atoms when they're bonded to other atoms. If you need a number, to sort of wrap your mind around this, an ionic compound could be something like where we take, sodium or lithium or something where the electronegativity is more like, point, I don't know, 9 or something like that. And the electronegativity of fluorine is like 4.2. So that's a pretty decent difference. But like if we're going to bond something like hydrogen and fluorine, and hydrogen's like 2.0 and fluorine's 4.2, it's a little bit smaller, but it's a pretty decent amount all the same. This is something that we refer to as polar. So polar covalent and non-polar covalent molecules that are bonded, they're sharing electrons. They're either sharing them equally or near equally, or they're unequal sharing, where one of the atoms is kind of hogging the electron density. So, in terms of what this could look like, so let's just draw out sort of some of our symbology for this. I could take the hydrogen fluoride bond, and I could be like, all right, well, that little stick between the H and the F represents 2 electrons that are being shared. We could indicate which one of these atoms is yanking on the electron density a little bit more fiercely by putting this little dipole symbol in there. The head of the arrow is indicating the center of partial negative charge. So this isn't like a formal negative charge. We use this little delta symbol, means partial or a fraction of, in other words, negative charge. Because the fluorine is yanking on the electron density. It's like a tug of war, right? Imagine that the 2 electrons that are being shared between those atoms are the rope in the tug of war, and fluorine is kind of winning, right? Hydrogen, therefore, has a partial positive charge. And so we say this is going to be a polar covalent bond. And we care about this because if we want to do chemistry with these molecules, we need to know, say, where's, the hotbed of electron activity? Can I use that to attack something else? In organic chemistry, we use electrons to attack other things and form new bonds. And also, we could use it, say, in acid base chemistry and say, hey, how strong is that bond? how partially positive is that hydrogen? How likely is that molecule to dissociate, or could we deprotonate that, right? We'd be plucking that hydrogen off. So there's a lot of questions that you can ask about the behavior of some of these molecules based on the type of bonding that we see in them. So we're going to be going through and I guess mostly focusing on covalent bonding, even if we draw polyatomic ions, because they are covalently bonded species. They just happen to have a charge. And then also neutral molecules. So how do we do that? Well, we need a model for drawing out these particular species. And this dude, Lewis, came up with a model for drawing out these elemental symbols indicating just the number of valence electrons with dots. So, for example, we could take something like hydrogen. With one valence electron, he's like, all right, put an H for hydrogen and then put a little dot next to it. And that's going to say, hey, there's my valence electron. This is what I have to bring to the party. This is what I can share, right? We move over to, say, I guess we move down to lithium, same group, one valence electron, one dot, right? Beryllium, two dots. You can put both on the same side, you can spread them out. It doesn't matter at the end of the day. It's just a cartoon version of what we might be able to sort of, I don't know, envision for these elements in terms of their valence electrons. Why do we only care about the valence electrons? Well, it's because those are the electrons we're going to use for bonding. The core electrons are sort of protected, right? They're closer to the nucleus, and they're just a little bit too attracted to the nucleus to just be involved in bonding. Then we've got boron, moving just across the second period here. We're over in group 3, so 3 valence electrons. Another trend on the periodic table is that the group number and the number of valence electrons match for main group elements. Carbon has 4 valence electrons, 4 dots. Nitrogen has 5. One other trend that you'll notice across the second period is that in addition to an increase in electronegativity as we go across, which you'll notice is going from carbon to nitrogen to oxygen to fluorine. Carbon has a tendency to form 4 covalent bonds and hang on to 0 non-bonded electrons. Nitrogen has a tendency to make 3 covalent bonds and hang on to 2 non-bonded electrons. Oxygen has a tendency to form 2 bonds and hang on to 4 non-bonded electrons. And then fluorine has a tendency to just make 1 and then hang on to 6 non-bonded electrons. So it kind of goes with that increase in electronegativity. You'd notice the bonding pattern with these. And when we draw out the Lewis structures, I'll show you the formal charge calculations and how we sort of connect those ideas together. So we have these little dot structures. This is Lewis's model for indicating the number of valence electrons. When we want to put these things together into a structure, we can start out first, I guess, with just an ionic compound. Because it's really easy to see how these get formed, a binary salt, right? So just something like lithium fluoride or sodium chloride or something like that, with using these dots. So you get an ionic species here, and say we want to take lithium with its single valence electron. We're going to add this to fluorine. So in Gen Chem, you probably learned, okay, we're going to have to ionize these. We're going to have to put them in the gas phase, right? So then we're going to have to, if fluorine is existing as a homonuclear diatomic species, then we got to cleave the covalent bond. All these steps have to be included and calculate the lattice energy and blah, blah, blah. Well, right now, we don't really care so much about all of that. We're just saying, hey, we're going to take lithium and we're going to take fluorine, and we're going to form lithium fluoride. The metal has a much lower electronegativity than the nonmetal, so that's going to be the species that gives up its valence electron, and when it does, it forms a positive charge. It loses an electron, it gains that positive charge, Who is going to gain the electron? The nonmetal. So fluorine is gaining lithium's valence electron. So now instead of 7 electrons around it, it has 8. And it's going to gain a negative charge. But we usually just write this as just LiF with no stick. Notice how there's no stick between these, no bond. Because an ionic bond is just an electrostatic attraction, right? So these are kind of like when your sock gets stuck to a towel, right? Static cling kind of a thing. With covalent bonding, it's a little different because we actually are going to have these 2 atomic orbitals overlap, and they're going to share space in a molecular orbital. You can still use the Lewis dots to do this, but I could take something like carbon with 4 valence electrons, and I can take 4 hydrogen, each with 1 valence electron, and I can make a molecule where we're sharing instead of donating these valence electrons. Or this is the moment where we actually do draw the little sticks in, and each stick represents 2 shared electrons. So notice like this is a covalent bond, that little stick there, they're sharing electrons. We didn't just donate electrons from one species to the other. The electronegativity of carbon is pretty close to the electronegativity of hydrogen, so we in fact have a relatively nonpolar covalent bond. And this is pretty easy for molecules that, we're just matching up dots here, right? But it can get pretty complicated pretty quickly. So we have a method for drawing out these Lewis structures. Because what happens when we have molecules that have double and triple bonds, right? Or what happens when we have a covalently bonded structure that has a charge, like a polyatomic ion? Or what happens when you can draw a bunch of different structures that are all electronically equivalent? We've just moved the electron density around. In other words, we're drawing resonant structures. So let's just get a couple of examples in. This is, again, just a review for how to draw these Lewis structures. So I could take a molecule like ammonia, for example. And what I like to do, and you can use the dot model if you like. I think it gets a little kind of messy after a while. Dropping a dot here or there gets a little tricky or whatever. I think it's better to put these together, just assuming that, again, in the Lewis model, we're going to be pairing up the electrons. So if you're pairing them up anyway, and each bond is a pair of electrons, why not just add up all of the valence electrons in the molecule and say that's going to be my electronic currency. It's kind of like I'm going into a coffee shop to buy a cup of coffee, and I need to have a certain amount of money available to do that. When I build this molecule, I need to have a certain number of valence electrons available to do that. So I'm going to add them up. The nitrogen has 5 valence electrons. It's in group 5. I have 3 hydrogens. Each one has 1 valence electron. And so this molecule has a total of 8 valence electrons. So again, just outline, this is coming from the nitrogen, and this is coming from the hydrogen. The 3 is 3 hydrogen there in ammonia. The next thing you need to do is decide what the central atom is going to be when you build the molecule. Well, it can't be hydrogen, right? Because hydrogen only has 1 valence electron to share. So it's not like it can have multiple things bonded to it. It can make one single covalent bond. So hydrogen follows what we call the duet rule. It will have a tendency to surround itself with 2 electrons. Everybody else has a tendency to, at the very least, surround itself with 8 electrons. And that's what we call the octet rule. And that goes pretty strictly followed all the way up to neon. Anything after neon, however, can enjoy what's called the extended octet rule. And there are certain elements that can accommodate more than 8 electrons, and it's totally okay. In organic chemistry, we have a tendency to focus mostly in the second period And so we have a tendency to really zero in on the octet rule. Nitrogen is going to be our central atom here. And we're going to basically start out with these 8 valence electrons connecting all of the outer atoms to the central atom. In this case, all of the outer atoms amount to 3 hydrogens. And when I did that, I used a single covalent bond to attach each hydrogen to the nitrogen. Each one of those covalent bonds represents 2 of the valence electrons. So effectively, I have used 6 of my 8, and there are 2 left over. Then you look at the structure and you're like, all right, all of the hydrogens are surrounded by 2 electrons. So the duet rule has been fulfilled for hydrogen. Nitrogen, on the other hand, in the structure that I have right now, only has 6 electrons around it. Nitrogen is in the second period and very strictly obeys the octet rule. So with these 2 leftover valence electrons, I'm going to complete nitrogen's octet by putting 2 dots, or in other words, a lone pair of electrons. And I've used all of the valence electrons that I had available to make that structure. So now I look, the first thing I want to check is to make sure that everybody has got either the duet, if you're a hydrogen, fulfilled, or the octet. And even if it's something big like phosphorus or sulfur or arsenic or whatever, you want to make sure that you at the very least have 8 electrons around your element. Nitrogen has 8 electrons around it. The next thing you want to check is the formal charge. Formal charge is going to describe the electron environment around each species. And so you really only have to do one calculation for each unique element in the structure. And as a reminder, I guess up here I can just write what that is. So the formal charge calculation, and probably in your textbook would be something like the number of valence electrons, and this is going to be for each of the atoms, minus half the number of bonded electrons minus the number of non-bonded electrons. You can also say, or for main group elements, we could say this is equal to the group number, half the number of bonded electrons. Isn't that just the number of bonds, right, that you see, the number of sticks? So minus the number of covalent bonds. So single bonds count as 1, double bonds count as 2, triple bonds count as 3, right? That kind of thing. The non-bonded electrons in Lewis models are dots. So the number of non-bonded electrons on the atom would be the number of dots. And this is just, I mean, it all means the same stuff. It's just when you're doing the calculation, it's a little easier in my mind anyways to say, I see a nitrogen here. It's in group 5. So in other words, it has 5 valence electrons. I'm going to subtract half the number of bonded electrons. I see that each bond has 2 shared electrons, so 2 bonded electrons. I see 3 of them, so that's 6 total, times a half is 3. Or you could just be like, I see 3 sticks coming out of the nitrogen, right? So 3 covalent bonds. The number of dots I see on the nitrogen, or the number of non-bonded electrons, is 2. And so there's no formal charge on that nitrogen. Each of those hydrogens is the same. So we only have to do one calculation. 1 valence electron. Each hydrogen has 1 covalent bond and 0 non-bonded electrons, or 0 dots. So there's no formal charge on the hydrogen. And so we have a valid Lewis structure. We have minimized the formal charges. So the best Lewis structure is going to be the one that minimizes formal charges, not necessarily the one that totally eradicates them. You do have, molecules out there ozone, for example, you just can't get rid of the formal charge, and that's okay. But you want to at least try to minimize, without doing anything blasphemous like, messing around with the valency. So, like hypovalent or hypervalent situation where you either have too few or too many electrons around an element, that's not okay. But if you end up with a Lewis structure where everybody's octet is fulfilled, hydrogen's duet is fulfilled, and we haven't, and we've minimized formal charges, then sometimes, if they're still there, it's okay. Let's do an ion. So we'll do a polyatomic anion. So let's do this. We'll do carbonate. So same thing, number of valence electrons. I'm going to count these up. So we've got a carbon, 4 valence electrons. We've got 3 oxygen. So there's the 3, and each oxygen is going to have 6 valence electrons. So it's in group 6. And then you see this -2 charge. When you're drawing the Lewis structure for either an anion, a cation, or an anion, you want to either add or subtract valence electrons to ensure that whatever structure you end up with at the end of all of this, you either have, a -2 or a -1 or a -3 or a +1, whatever. So in this case, we're adding electrons, right? Valence electrons. We want to make sure that we end up with a -2 charge. And each electron has a -1 charge. So I'm going to go ahead and I'm going to add 2 to make sure that whatever structure I come out with has a -2 charge. So let me go ahead and label this. This is the number of valence electrons in the carbon. This is going to be the number of valence electrons for each of the 3 oxygen. And then this 2 is going to be the charge. That's our -2 charge. So the trick to deciding your central atom, so the one with the hydrogen is easy because hydrogen can never be a central atom, right? But carbon or oxygen can. And so normally what you'll do is say in these molecular or ionic formulae, the very first element that you see generally is your central atom. Or you could say, I'm going to pick the most electropositive element, and it's going to be the central atom. So for this structure, my carbon's going to be my central atom, and I'm just going to go decorating my central atom with all of my outer atoms. In this case, they're all the same, they're oxygen. So when I add up, I forgot to total up my number of valence electrons here, I get 18 and 4 plus 2 is 24 valence electrons, right? That's right? 18 and 4 is 22 and 2 is 24, okay. And so I've used up, so I got 3 covalent bonds there. Each bond is 2 electrons, so I've used up 6 of my 24 valence electrons, which means I have 18 left over. And then just a quick inspection of this. Nobody's octet is fulfilled. Both of these elements, carbon and oxygen, are in the second period, so they strictly obey the octet rule. So what I'm going to do is, what I've noticed when I take my central atom and make it the most electropositive, that sort of makes my outer atoms the more electronegative elements. So what I decided to do, just in a series of just steps, like a recipe to put these things together, when I have extra valence electrons and everybody's octet still needs to be fulfilled, I begin with the most electronegative element. So I'm going to dot up, oops, sorry about that. I'm going to dot up each of the oxygens to fulfill their octet using all the leftover valence electrons. So I have now used up all 18 of those valence electrons, make that look like a 0. And so what I've done here is I've fulfilled the octet for all the oxygens, but look at how the carbon is still hypovalent. It only has 6 electrons around it. So we already, this can't be a valid Lewis structure because, carbon's hurting for some electrons. But we start drawing these structures first with single bonds. Double and triple bonds come in later when someone needs electrons. Like in this case, carbon's going to need some electrons. But let's first do a formal charge calculation to just see how bad it looks. So we'll do the formal charge calculation for the carbon. 4 valence electrons, 3 covalent bonds, 0 non-bonded electrons. We have a positive 1 charge on the carbon. And each of the oxygens in this particular structure is equivalent. So we'll do one calculation that will represent all of them. So just looking at any one of those oxygens, we see 6 valence electrons. It's in group 6. Each of the oxygens has a single bond and 6 non-bonded electrons. So each one of these oxygens has a -1 charge. So first of all, carbon is hypovalent. So that's right away, we don't even have a valid Lewis structure. Number 2, everyone has a formal charge. So this is a hot mess, right? In order to fix this, we're going to share some electrons between one of the oxygens and the carbon. And when you do that, you get this. So we got a double bond between that oxygen and the carbon, and still 2 single bonds to these oxygens. We haven't done anything to them, so you can expect that their formal charges will stay the same. But we have affected the electron environment around the oxygen on the left and the carbon. So we're going to do another formal charge calculation. Carbon has 4 valence electrons. There are 4 bonds here. 0 non-bonded electrons. There's no more formal charge. The oxygen on the left needs to have a calculation done for it because we have shared electrons between it and the carbon. So we may have changed the electron environment around that particular species. 6 valence electrons for that oxygen, right? 2 bonds, you see the double bond, and there's 4 non-bonded electrons. So, sorry, my cat is being very noisy right now, sorry. So here we have no formal charge for the carbon, and the oxygen on the left now has no formal charge. You might be tempted to make another double bond, right, and try quenching those negative charges on the oxygens. But here's the thing, carbon already has 8 electrons around it. So you can't make another double bond in addition to the one that you already have. What you can do is you can move the double bond. So I could say, well, let's put the double bond here instead of on the left. But when you do that, instead of putting 10 electrons around carbon, you're going to push these electrons back to this oxygen. We get what we call a resonance structure. So this is a special arrow here. All we're doing is moving the electron density around. The overall net charge on the species will be the same. And if I can do that, then I can do this. And I get another resonance structure. So all of these are valid. Notice how all of these actually amount to a -2 charge on the entire species, which is kind of what we wanted, right? Because we have a -2 charge on carbonate. But these are all resonance structures. In organic chemistry, it's going to be important to us to recognize when we can draw these, because it's going to be really helpful for figuring out why, or possibly why, things add to other molecules in certain positions. We can talk about things like the most contributing resonance structure. So when you're looking at, a synthesis and you see a product, you're like, where the heck did that come from? Oh, I can draw a resonance structure for this over here. Now it makes sense why this looks the way it does, kind of a thing. So we'll be bringing up the term resonance structures very often. Let's see. You can do a calculation on these species and you can get a feel for, say, from Gen Chem, you remember that single bonds are longer and weaker, or they have less, energy about them than a double bond, which is shorter, right? So you'd expect that if you were analyzing bond length and strength, or in other words, bond energy in the carbonate anion, you see two single bonds and a double bond, you'd expect to get two values, right? One for the carbon oxygen single bonds and then one for the carbon oxygen double bond. But in reality, what you get is a single value, and it's some weird average between all three of those bonds, a double bond and two single bonds. And so what you can do is you can draw a hybrid where you're going to basically indicate that the double bond could be anywhere with these little dotted lines. It's just a better representation of the data, and we put the charge on the whole species on the outside. So you sometimes might see something like that. But for organic chemistry, what we really want to focus on is the fact that resonance structures do exist. And it's not just that they exist and that we can draw them, it's what kind of information can they tell us? Very often they can help us out when we're trying to decide where an incoming group is going to add when we make new bonds or new species. So that's going to be it for just sort of a Gen Chem review of Lewis structures. What I'd like to do is, in the next video, introduce you to the concept of hybridization. So there are moments where, like up here, when we drew methane, it looks like carbon has formed 4 covalent bonds, right? There are 4 hydrogens. There's 4 valence electrons on carbon. Each hydrogen has a single valence electron, and you'd think by the Lewis model, hey, sure, no problem. Let's just make 4 single bonds on the carbon, attaching each of those hydrogens, and it seems like no big deal. But then when we start talking about like how we feel bonds might be formed, and we start looking at the valence electrons on an energy level diagram, say for carbon, you'd notice that we've got two of the 4 valence electrons are paired up in the 2s orbital, and then the other 2 valence electrons are occupying 2 of the 3 p orbitals singly, right? So all alone. So in other words, you've got 2 half-filled p orbitals, and we imagine that we have 2 bonding options. Either we're taking an entire empty orbital and allowing somebody's full orbital to share, or we're going to take 2 half-filled orbitals and allow them to overlap and share. And in the case of carbon and hydrogen, well, hydrogen has a half-filled orbital, or it only has 1 electron all by itself, unpaired, in the 1s orbital. But carbon has 2 paired up electrons in the 2s orbital and 2 unpaired electrons, 1 each in the 2p orbitals. So how is it possible that we could bond 4 hydrogens with a single carbon? Wouldn't it make more sense to have a lone pair, the 2s 2 electrons on the carbon, and then just 2 covalent bonds? So then what happens to the other 2 hydrogens, and how is it possible that methane exists? So you'll find in chemistry that we make these models and they work really well until they don't. Lewis structures work really well until something like this pops up. And you're like, well, how electronically do you explain the fact that not only do we have 4 bonds off the carbon, but they're not 90 degrees? A crystal structure of methane shows us that they're actually 109.5 degrees. How the heck does that happen, right? So we have a new model that we have to look at, and we have to talk about hybridization. So we're going to do that in the next video.